Let's begin with the actual segment for right now, which is Waveform Basics. Now, I have here a setup on the screen that shows a little oscillator, plus it's setup and some things just to generate some sounds. Good times. The idea, actually it's funny, I saw this tutorial that someone made like 2 or 3 days ago about waveforms versus sound waves. And it's kind of interesting that you would want to separate the two, which I guess technically is true, but this is sort of an interesting concept. And this is like the most pure basic idea of how sound works and how we hear sound, how there's waves happening in the air and that kind of thing, and you get to our ears and that sort of deal, and what this represents when we see it on an oscilloscope, which is to say something that can show us an oscillation. And what is an oscillation? Well, an oscillation is something that oscillates, just moves up and down. That's all there is to that, just does this. That's actually what speaker cones do when they create sound. And the whole idea is that it moves back and forth to create movement in the air, which pushes air and then stops pushing air and stops pushing air again and that kind of thing. And that change in air density moving through space is a sound wave. And the waveform through the speaker cone is what creates the sound wave. So for example, what we're looking at here, which I can right there. That is a sine wave. It's one of the 4 basic waveforms. Individual sine wave represents one individual frequency. A frequency is how fast the waveform is oscillating, which is the measurement of its value, its tone. And there are other measurements that could be applied to any kind of sound, like amplitude, just how loud it is, that kind of thing. But one big important part about sort of a waveform is this idea of speed and pitch, which essentially what it means is that if it's higher in pitch, it's just going faster. And if it's lower in pitch, it's moving slower. And that's really all there is to that. You might have been thinking, well, obviously, but that actually will become super duper important, especially when we start talking about FM later. I was going to say something about, I have notes here. We'll get to that. So we have the sine wave, another of the 4 basic ones. Actually, I like citrus for this particular purpose. That's the wrong operator. There we go. Actually, I did remember the thing I wanted to talk about, and that's this idea of using oscillators for more than just sound. In the analog world, every kind of control source is some kind of oscillation. And as producers, you may be familiar with the concept of an LFO, which stands for a low frequency oscillation, or a low frequency oscillator. And then you can put that to a parameter and you can make it move around and move up and down just in a repeated constant motion that you have control over. And in sort of like the analog world, that's the difference between a low frequency oscillator and just your regular average oscillator is there's no difference. They're the same thing. It's just one happens to be really, really slow. And there's a classification for how slow it is. The low frequency oscillation is where it's too slow for you to pick out a tone. You're not able to determine that it's a note anymore. You're actually able to hear individual movement as opposed to it's so fast that it sounds like one note, which is what's referred to as audio rate oscillation, which is again something that'll become super important when we start talking about FM, which seems interesting that I'm laying all this out now, even though we're not talking about FM until tomorrow. But it makes sense, believe me. Anyway, this waveform that we're looking at right now is a triangle wave, which is just pretty easily seen why. One thing I wanted to show when I play these things on the screen is that the sort of the harmonic content of the few. I mentioned when I play a sine wave that it represents a single frequency, and in the equalizer beneath citrus we can see that it is in fact a single frequency. Pretty straightforward. However, look at a triangle wave. While still a single frequency of the waveform, and it is the same oscillation over and over again, we have more than the one frequency. We have a whole bunch of different frequencies. And these are harmonics. And these are this harmonic content is what builds up to create the waveform that we see, which become super important when we talk about additive synthesis. kind of give you a little preview of that. That's a saw wave, that loud guy right there. A saw wave is a very interesting waveform to look at for a lot of reasons. Primary one being that in the concept of subtractive synthesis, a saw wave is pretty much king. And the only other sort of important waveform that is present for this concept is the next one that we can look at, which is a square wave. But look at the harmonic content of a saw wave for a second. It has a lot of harmonics, a lot of them. But then watch what happens when I go to the square wave. It sort of loses some harmonic value, and it appears to be of an even kind of way. It turns out it has half as many harmonics as the saw wave does, and that'll come in handy again later. So many things, all of these things will build up to such incredible, ridiculous things that you would never have thought of. Unless you already know this stuff, in which case you know what I'm talking about, and you should be excited. But let's go back to the saw wave for a second, because you may see in the citrus window versus what we look at in the oscilloscope, that the oscilloscope has this kind of mess going on. This kind of glitchy business happening near the tail end of it versus the perfect, just wall of sound that's supposedly what a saw wave is. And this actually has to do with the next thing that we'll talk about, which is the concept of band limiting, which is in relation to how digital sampling works as a whole, which is super freaking cool. A lot of people have this idea about sampling in relative to analog playback, like tape or a record or something like that. And they have this concept of sampling and being, well, okay, you're taking little moments of sound data so many times a second, as it turns out, on average, 44.1 thousand times a second, which is a lot, that is just taking little bits, and it plays it so fast that we're not able to tell that it's taking little bits, that kind of thing. But with this idea, we're still taking just little bits. It's not the whole thing. It's not everything. We're losing information. And that's not entirely true. Sometimes it's true, but for the most part, not so much. And we can look at this by observing the recording of a saw wave in a different environment. So I'm gonna get rid of this for a second. We're gonna open up Edison, and we're gonna record a saw wave. Boop. So if I zoom in far enough, we can actually see that mess that we're looking at in the oscilloscope. But if we zoom in far enough, we can see the individual samples. And then we see kind of the source of the mess, the fact that the sharp fall off of the saw wave is not actually as sharp as you might have been led to believe. It's a bit different for every plugin that generates a saw wave. They're not all the same, but for the most part, they're pretty similar. They have this sort of business going on. But one thing I want to look very closely at is how these little dots, these samples, are behaving with the line that's going on behind it. So with that line behind it is actually the waveform that's being put into the speaker for it to move to create the sound that we're hearing. That's the signal, that's what's going out. Now, how did it know to make that signal? Which is an interesting question, because if you look at the dots, some of them are like in the middle of the curve, or like there's a curve between it and the next dot. Like they're not straight lines in between the dots. They don't, like, where did that information come from? How did it know to put a particular movement in between those points? And this has to do with the concept of band limiting. As it turns out, when you're doing sampling of a recording or a generation of some kind, what it's doing is it's solving for these points. It's essentially playing connected dots with the points, but instead of just drawing anything that could possibly fit with the points, which you could do yourself and you could just do whatever you want, it has one constraint, and that's the band limit. And the band limit is essentially the highest frequency it's able to produce. And this is what's referred to as the Nyquist limit, which is the highest frequency you can have given the sample rate, which is half the sample rate. So for 44.1 kilohertz, which is what we're doing now, the highest sample rate is half that, which is 20.05? Yes, math. I do math. So, just a bit above the limit of human hearing, which I have to imagine is the purpose of having chosen that as a standard, just to make it easy. You can, of course, have higher sample rates and have higher frequency response, and that whole deal. But what this means is that when connecting the dots, if you were to move even a little bit from this particular configuration of samples, it would create frequencies higher than Nyquist. And it knows this. So when it solves for these points, it has to solve for a particular solution that creates a sound that does not go above Nyquist, of which, with these samples, there is only one. And this is what it does, and this is what it is. This is a little bit more impressive when it comes to analog recording. I got all this information that I just said to you from a video a guy did on ziff.org. Just YouTube ziff.org sampling, you'll find it. It's pretty great. And he had his whole setup where he had an analog oscillator run through sampling, going back out to an analog oscilloscope. And it was noted that if you put out like a 1 kilohertz sine wave, it came out a perfect 1 kilohertz sine wave on the other end. Which is to say that sampling is more than good enough to recreate basically what we're doing. Except for when we get to something like a saw wave. A saw wave is an interesting sort of case study for the limits of sampling, but then also kind of the limits of just sort of speakers in general. Because if you think about what a saw wave does, or a square wave even, it's kind of physically impossible for a speaker to do that. Because the perfectly straight line of being like, here's a point, here's another point, they're technically the same point in the same time, but they're two different places, and the speaker cannot do that. It will try to do that as hard as it can, but and then if we were to record the result, it will look something like this, which is why the playback and recording of a saw wave in a synth is usually something a bit more benign, like this particular thing. And of course, this limitation that we're looking at is basically the result of band limiting. Is that with the line that an infinitely straight line would mean infinite frequency response. And if we had infinite frequency response, then we could do that, because that could mean that the speaker is moving infinitely fast to create as high a frequency as we could possibly imagine. And that would result in your perfect saw wave, but that's never going to happen. And this applies to kind of mastering as well, which is not something you might think of. Because sometimes when you're mastering a track, it might occur to you, why don't I just let it clip? Because it sounds kind of cool when I let it clip. I've done this, and I've learned why. And this is because when you clip something, you get perfect digital distortion, which is to say that you're making a signal now that has created ultimate square waves. And like we just said, speakers can't really react to that uniformly. So while it might sound okay in your particular setup's attempt to recreate it, it's not going to sound wonderful in everyone else's. It's not going to be consistent. But a thing like this particular kind of solution to something like that, will sound uniform because it's 44.1 kilohertz band limited. And pretty much even the shittiest of iPhone solutions will be designed to work with 44.1 kilohertz as sort of the standard. And, movies like to use 48 kilohertz, and then you can use 96 or 192. You can keep going higher. And then but you're still going, if you zoom in far enough, you will still just have this sort of look at a saw wave. But of course, it's playing so fast that we really can't tell anyway. But it's kind of important to know about that. So before I talk about bit depth, does anyone have any questions about all that we just talked about?
I
Cool.
think we're good.
Yeah. I like explaining that stuff. It's just so good. So bit depth is kind of important. For the most part, playback-wise, it's not super important, just because you're going to have 16-bit or 24-bit. That's pretty much it. But in FL and some other DAWs, there's actually a third option internally, and that's also, you can render it as well, and that's the 32-bit wave file. That's not 32-bit or 64-bit in terms of x86 processing or whatever. It's 32-bit depth. Bit depth is the measurement of how many sort of stops there are in volume reaction. A good way to visualize this would be with the wave shaper. There's a little line type I like to use, the stairs mode. Here we go. This is kind of what bit depth represents, from whatever its lowest silence measurable level is to 0 dB, sort of the maximum standard. How many different levels of volume can there be from negative infinity to 0? Bit crushers reduce this amount, which is why it sounds the way it does. Like, if you make something sound 8-bit, 8-bit is referring to the fact that it had 8-bit depth, which wasn't super significant. And there was other, qualifiers to that existence, but this is more or less what that means. 16-bit, And like the way that bits work, it's a kind of a math that I'm not super familiar with, but anybody who's ever had any kind of computer science will know that the difference between 16-bit and 24-bit is not a linear relationship. It's one where the amount of stops in 16-bit is a lot already, and the amount of stops in 24-bit is a lot more than just the fact that 24 is more than 16. There's numerably it's a large amount. And the whole point of this is that it increases the possibility for dynamic range, which is the idea that we can have a quiet, it can swell up and down, and then that swell will not be jaggedy and stupid sounding because we have enough stops of volume for it to interpret a level of volume for each individual moment in the sweep, so it can go from pretty quiet to pretty loud and not, break things. 32-bit is insanely more than that. And the functional difference between 32-bit versus 24-bit and 16-bit is that 24-bit and 16-bit, they stop at 0 dB. That's kind of their limit. And for playback purposes, that's everything. MP3s, FLACs, that kind of thing. Everything plays back and stays at 0 dB, and that's pretty much it. But 32-bit keeps going. It doesn't actually stop at 0 dB. It has the same kind of density of measurement from the negative infinity to 0 dB, but then it just keeps going. And the importance of this is the idea that when we look at like the mixer in FL Studio, for example, if I had a signal in somewhere other than the master, right now it's not clipping, but I can make it clip. So right now that channel is going above 0 dB. It's going above 0 dB and it's going into the master. And if this were a purely 16-bit or 24-bit world, what that would mean is that it's clipping and I've lost that data that went above 0 dB. It created those perfect distorted square waves I mentioned earlier. But because it's going to 32-bit, somebody who I trust on the matter once told me that the limit to 32-bit is something like plus 1600 dB, some stupidly high amount that you would never reach unless you actively tried to. And even then, some DAWs might not even let you, just because it's just so loud. But the purpose of this is that you really don't need to worry about things like we look at you talk to mastering engineers, they tell you stuff like, the kick needs to be at minus 6 dB, the vocals need to be at minus 8 dB, and like everything needs to be at all these particular levels, and all of them need to add up to be less than 0 dB, so that when they master it, it's not clipping, that kind of thing. But for 32-bit, and internally anyway, it doesn't matter at all. It matters only for your own listening sensibilities where things are that the mix sounds good. You don't need to worry about measurement even until the very end of your actual mastering chain where it goes out, because chances are your playback, even on the audio interface that you're running, even on this guy, the playback is still 24-bit or 16-bit. So even if internally it's not clipping, you're going to hear it clip. But if you were to save it as a 32-bit file and you have peaks that go above 0 dB, those peaks are still there. They're not actually distorted. They're not actually gone. You can turn it down and you can bring it below 0 dB and it'll be fine. It'll be its pristine original self. And along with that, you can bring the noise floor down farther than anyone could possibly think about because of the whole 1600 dB headroom thing. Which one day I'll do an experiment to actually see that is what I'm talking about. But for the most part, people tend to stick around the whole 0 dB limit because that's the standard. And that's sort of how that works for playback of 16-bit and 24-bit, literally everything else. There are 32-bit interfaces. I have no idea how they work. I have to imagine they're really fun. Because I like things loud, as do most of humans, it turns out. Actually, there is the whole psychological concept of the fact that loudness, even if it's the same sound, you will think it sounds better. Like your brain will be like, that's better, whatever that is. I like that better, even though it's like the same thing, just louder. It doesn't particularly matter much. Now, all of that was a nice primer as to how digital anything works, which is cool to keep in mind, especially when we start talking about whatever kind of synthesis we're doing versus the analog versions. And a lot of people will get it in their heads that we just cannot match the fidelity of analog anything, and that's just not true. We might not be able to get exactly sort of identical to some certain things, but you wouldn't really get exactly identical to certain digital things either. So don't worry about that too much. Don't worry about that too much, because I use words, I promise. All right, so now let's actually finally start for real to talk about subtractive synthesis. The only weirdness is that when you actually use the wave shaper with the steps to do that, it doesn't sound anything like bit crushing as we expect it to. Because bit crushing effects and VST, like in VST versions or even like in plugins, they do that, but they do it with different kinds of like shaping and different kinds of algorithms to make it not sound painful. Because it will if you do it with the wave shaper, which I guess does not. Which I prefer, honestly, that it just does what it's showing you that it's doing.